Welcome. We are looking at the bulk free energy density, and that is an expression that I am going to approximate by using a c squared into 1 minus c whole squared. So, there are certain transformation which you can do to the regular solution model to regular solution like free energy to get to this point. But one more point that is important to remember is that the regular solution free energy is not just a function of composition, but it is also a function of temperature. So, when we are doing this, we are assuming isothermal. In fact, for the rest of this course, I am going to deal with only isothermal cases. Okay. Now, isothermal is not something that you can assume. For example, if you are looking at a problem like solidification, the main problem, for example, pure material solidification, the most important thing is the heat removal from the interface where there is latent heat evolution, and that is what leads to interesting microstructural features and so on. So, there you cannot assume isothermal, but by the same token that is a case where you cannot use a free energy functional anyway. You have to use an entropy functional and you have to form a phase field model which is consistent, thermodynamically consistent. So, but we are going to assume for the rest of this course that everything is isothermal. So, what does that mean? So, that means that we have a phase diagram. So, for today's lecture, for example, we are assuming a phase diagram which has a miscibility gap like this, because and we are looking at a region which is the spinodal region, right. So, in this region now we are going to assume that I am going to be always at some temperature T. So, this free energy expression is corresponding to some time T. Now, at that temperature the two end compositions are not going to be 0 and 1. So, it could be for example, some 0.1 and it could be 0.9, but this function stretches the 0.9 to 1 and 0.1 to 0 and makes that transformation. So, that is one of the transformations, and it makes sure that the maxima is at the center. And if you look at the free energy at this point, so there is a barrier that has to be overcome, and that barrier is what we are trying to approximate with this functional form. Okay. So, we have made the assumption of isothermal. So, the free energy is no longer a function of temperature, it is just a function of composition. And the free energy had two terms. So, one is the bulk free energy density, which is what we are approximating using AC squared into 1 minus C whole squared. There is the gradient term, and in non-dimensionalized case we are going to take this A, that kappa, that m by nv into f double prime. So, everything to be equal to 1. So, that is what we are going to do. Okay. So, let us take a look at this function. So, I am going to first plot this function. So, I am going to use the computer. So, as usual we open a terminal and I go to the directory in which I have okay. So, this is always important. So, and then I invoke Octave from this terminal. Okay. So, first what I am going to do, I want to plot this function AC squared into 1 minus C whole squared. So, I am going to define C to be a vector which goes from so, let us go from minus 0.1 in steps of 0, 1 to 1.1. Okay. So, that is C. We need to define what is A for defining. So, let me define A to be 1, and now I am going to define F to be equal to A dot star C dot star C dot star, because I want to take each component of this vector C and I am going to calculate an F dot star 1 dot minus C dot star 1 dot minus C. So, that is the F. Now, I can plot C comma F. Okay. So, that is the function that we have. Okay. So, as you can see, so it has a minima at 0, it has another minima at 1, and it has a maxima at 0.5. Now, you can change the A value you can make A to be 2 for example, and you can define f, and you can. So, before I do that, let me hold on, so that the previous plot will be retained, and on the same plot I plot this, right. So, I have the other curve. So, let me plot the second curve using a red line. So, we know which is corresponding to A equal to 2. So, you can see that A equal to 2 curve is the one which is having much higher barrier to overcome. Now, I can also do one more. Let me take A equal to 4 and let me define f, and let me plot in this case with a green line. Okay. So, now I have 3 curves. As you can see, A equal to 1 is this curve, A equal to 2 is this curve, A equal to 4 is this curve. So, when you have A equal to 4, it is like 0.25, that is where the maxima is. So, starting from 0 to 0.25. So, when A is 4, this is 4 by 16, and A is equal to 2, this is 2 by 16, that is why it is going somewhere around 0.125. And so, when A is equal to 1, it is 1 by 16, and 1 by 16 we can calculate, and that is 0.0625. Let us go see that this is 0.0625. So, if you move your cursor to that point, then you can see here in the bottom it gives you the value. So, it is 0.0625. In other words, the A value that you choose determines what is going to be the barrier height. Okay, this is very important to understand. So, there are 2 parameters which we are going to change during the simulations. One is A, the other one is kappa. What is the meaning of A? A tells that from this minima to this minima, you have to overcome a maxima in between, and what is the maxima point, how much is this barrier height is what is decided by A. So, if A is 1, it is 1 by 16, if A is 2, it is 2 by 16, if A is 4, it is 4 by 16. So, basically what we are saying is that A by 16 is the barrier height, and you can see very clearly from this figure that you have a minima at 0 and minima at 1, and you have a maxima at 0.5. So, this is the A c squared into 1 minus c whole squared curve. Now, what is of interest to us is f double prime, right. So, we wanted to look at, so it is m by n v f double prime for example. So, let us take this A c squared into 1 minus c whole squared. So, what is f prime? If you try to calculate, you can see that it is nothing but 2 A c 1 minus c squared minus 2 A c squared 1 minus c, right. So, you can now pull 2 A c into 1 minus c. So, that will leave with 1 minus c here and minus c here. So, that gives you 2 A c into 1 minus c into 1 minus 2 c. Now, the first derivative should be equal to 0 to identify, that is a necessary condition to identify the points at which the maxima and minima are there. So, if I equate 2 A c into 1 minus c into 1 minus 2 c to be equal to 0, I get the solution as c equal to 0, c equal to 1, c equal to half. So, those are the 3 points where the extrema are achieved. Now, I have to take this curve and I have to get the second derivative. So, let us take the second derivative. What is f double prime? F double prime is nothing but 2 A 1 minus c 1 minus 2 c minus 2 A c 1 minus 2 c minus 4 A c 1 minus c. Okay. Now, if you take the value c equal to 0, then these two terms go to 0. So, f double prime at c equal to 0 is equal to what? Is this is 0, this is 0. So, it is 2 A, and because A is a positive number, so it is greater than 0. What happens at 1? So, this term and this term go to 0, and this becomes 1 minus 2. So, there is a minus sign. So, that comes. So, f double prime at c equal to 1 is equal to. So, it is minus 2 a, c is 1, and so there is a minus 1 that is coming here. So, that becomes. So, that is also greater than 0. What happens at c equal to 0.25? So, f double prime at c equal to 0.5. So, 0.5, these two terms are going to be 0. So, I am going to get minus 4 a 0.5 and another 0.5. So, these are going to go. So, I get minus a, which is less than 0, clearly indicating that these two are the minima points and this is the maxima point. Okay. So, it is instructive to actually plot these functions also. So, let us plot the function f prime and f double prime. Okay. So, let me hold off. So, I do not want the earlier figure, I want to clear the figure. So, I want to define f prime to be equal to let me first define a equal to 1. Okay. So, we will do rest of it with a equal to 1. So, we know the f expression. So, that is the f expression. So, f prime is equal to a dot so 2 into a dot star c dot star 1 dot minus c dot star 1 dot minus 2 dot star c. So, that is f prime. F double prime, f d prime is equal to. So, that has 3 terms that we wrote down. So, we are going to use that expression. So, that is this term. So, we are going to use 2 so, we are going to use 2 dot star a dot star 1 dot minus c dot star 1 dot minus 2 dot star c, that is the first term, minus 2 star a dot star c dot star 1 dot minus 2 dot star c, okay, minus 4 into a dot star c dot star 1 dot minus c, that is f double prime. So, let us plot these 3 functions. Plot c comma f. Okay. So, you have the function. Now, plot c comma f prime with a red line. So, the prime is with a red line. So, you have this. Okay. So, I should have used to hold on and plot c comma f. So, I have I have the free energy curve, I have the derivative curve. So, you can see that the derivative go to 0 here and the derivative go to 0 somewhere here at 0.5 where the maxima is, and it is also going to go to 0 here at 1. Now, I am going to plot f double prime using green. Okay. So, you can see that this curve is going below 0 at in these 2 points. So, these points are basically the spinodal points. Remember that f double prime where it becomes 0, where it changes sign from positive to negative. So, wherever it is positive it is nucleation growth, wherever it is negative it is the spinodal decomposition. So, the spinodal decomposition point is somewhere between 0.22 or something, right. So, it is somewhere here and here. So, it will be symmetric about 0.5. So, if it is 0.22 then you have to subtract 0.22. So, somewhere about 0.78 is where this will be 0. So, these are the 3 curves which are of importance to us, and because this f double prime, the green line is becoming negative at this point, is why when it is multiplied by m by nv f double prime, the diffusivity is becoming negative. So, diffusivity will be positive here, will be negative here. And this is the negative diffusivity region that is of interest to us, because that is where spinodal decomposition is going to take place. So, basically if you find out the minimum points and plot, that is the phase diagram, and if you find out these double prime 0 points and plot, that will be the spinodal point. So, inside that will be the spinodal region. So, that is what we are going to look at in the subsequent part of this lecture. So, we are going to use for the rest of this lecture and most of this course the first term in the free energy functional, namely the bulk free energy density per atom. So, that F quantity to be AC squared into 1 minus C whole square without loss of generality. The reason is that the most important thing for phase separating systems is that there should be two minima with a maxima in between, and the simplest function polynomial which can capture this is AC squared into 1 minus C whole square. The reason why we are not using a logarithmic term or some regular solution like free energy is because numerically they are very difficult to deal with. When you integrate these equations numerically, you will find that it imposes a huge restriction on the time step that you can take for doing the integration. So, it becomes a little bit cumbersome. So, for understanding the phase field models, it is sufficient if you use this simplified function, but any other function is not going to change anything except to increase the complexity or the form of these functions. So, it is possible that you can take, if you know the real free energy, you can take that free energy and you can deal with it, you can work with it. So, there is nothing that stops us from doing that, but for simplicity's sake and to have for example, I want to change the barrier and I want to see what happens to the system and things like that. Those things are easier if we do it using the model free energy. So, we are going to stick to this model free energy. It is called a double well potential, because as you can see there are two wells in the free energy, one at 0 and one at 1. So, it is a double well potential, which is what we will use for the for almost the rest of this course. So, occasionally we might use some other functional, in which case we will write it down what it is, we will plot and see how it looks, but for most of the times, at least for the Cahn-Hilliard part of the equation, we will use the double well potential. Okay. So, next step is to see how the solution to the diffusion equation and the phase field equation are different. Okay. So, we have done this analysis, I think, as part of the diffusion equation. So, I will remind you of the analysis and we will proceed with the analysis in these two cases and compare and see what happens. Okay. So, that is what we will do in the next part of this lecture. Thank you.